Hi, everyone. Dr. Oz here. And here we are in week 4 of the 6 weeks that we will spend together during this Earth Science course. So this week I'm going to talk a little bit about plate tectonics, and then I have a little activity for you to do, which will be the graded portion of this week, and an interesting short video on why it's so difficult to predict earthquakes. And as you'll see, as I talk today, plate tectonics, of course, or where those tectonic plates lie, have so much to do with the creation of an earthquake. So we'll take a look at all of that today. Now, the first thing in the early part of the 1900s, we had a scientist by the name of Alfred Wegener. And Wegener, or Wegener, you might hear it pronounced in some places, published a book called The Origin of Continents and Oceans. And he was really the first to propose the theory of continental drift, right? That all of the 7 continents were once together in one supercontinent that we called Pangea. And eventually those continents split apart and drifted away from each other. And then the Ice Age and water and things came about, and we ended up with oceans and bodies of water. Okay. So that's kind of what we're going to look at. This whole Pangea piece was about 200 million years ago, just for some reference there. So here's a nice look at, Pangea, and you see that the continents kind of fit together like a puzzle. And this is what caught Wegener's eye. He began to look at the continents as we know them today, and he actually took a map and cut it up and was able, like a puzzle, to kind of piece things back together. And that's kind of what got his whole theory moving about. He looked at, how he could very easily put South America into Africa here. He also saw that the fossils that were located on various striated levels matched from continents that were separated by ocean water. Same thing with rock layers, that if there was sedimentary rock on one continent, even though there'd be a large ocean separating it from another continent, that sedimentary rock would be in the same location, except they were separated. So it kind of got him thinking, like, how did, for example, fossils of lions and things like that, how do we find fossils of lions in North America, but we don't ever see a lion itself? So, he used a lot of this information. Lystrosaurus was one of those first animals about 230 million years ago. And he kind of traced the movement of Lystrosaurus from one continent to the other, right? He was finding fossils of these animals, and they were land animals on continents that were very much separated. So, he started, that's really what got him thinking, like, how did this land animal get from one continent to the other when it was separated by a large ocean? So initially, Wagner was unable to prove how the drift occurred. Like he had this the continental drift theory out there, um, and it was initially not accepted because he couldn't prove why they drifted. Why did the continents drift? So he could not, provide any type of mechanism for why that continent happened to drift. Now, if we go back to the first week, we talked about the lithosphere, that outer, kind of rigid layer of the Earth. And in that lithosphere, we see several different plates. And this eventually became the mechanism for plate tectonics, right? That the movement of the continents happened along those particular plates. And the other thing that they knew, and by the mid 1900s, they were able to use submersible vehicles to go down into the ocean. And when they're mapping out the floor of the ocean, we're finding these separations. And so they knew that these plates did exist, and they are probably many of them covered in water. So they started to kind of map out, exactly where these plates occurred. And as they did that, they had to go beneath even the lithosphere. Remember, the lithosphere is that outer layer, and then beneath the lithosphere, we get that hotter, more molten rock layer. We get the asthenosphere. And in the asthenosphere, this is where the magma is located. And what we're going to see is when there's pressure and things like that, and we get that build up, this is what is going to make those plates move. All right, so we have our crust layer, we have our lithosphere, which is a very strong layer, and then the asthenosphere, which is our liquid layer, magma layer. It's much weaker than the lithosphere. So we determined that there were basically three types of layers of rock, and three types of plate boundaries, right? Two are really important. Ones that are divergent, which means those plates are moving apart from one another. The second is convergent, which means that the plates are coming together. And then we had some other types of plates that we'll take a look at in a second. So divergent, plates moving apart, spreading of the ridges in the ocean floor, all of those things start to happen, right? So we get movement here away from each other. Convergent plates, again, are those plates that are coming together. And these are going to, a lot of times, are the basis for the formation of our mountain ranges. So when the continental plates come together, two continents butting up against each other, what the theory tells us is as they come together, we get a push upward of that rock. And that is how we formed the mountains that we see, the Rocky Mountains, the Andes, the Cascades. All of those types of mountains were formed from the movement. The Himalayas, for example, it's another one, from the movement along plate boundaries. And then the third type is oceanic continental convergence, right? So we're going to have a continent moving, and that oceanic plate kind of falling down into the asthenosphere as the continent moves above it. So with our convergent plate boundaries, we have a couple different ways that this happens. We have what's called oceanic conversion. And this often is going to form our volcanoes. So that's something else that you can, take a look at if you're interested in things like that. You see a lot of active volcanoes that are right along the plate lines. Continental conversion is another. So here's where we have continent meeting continent. This is what forms not our volcanoes, but our mountain ranges like the Himalayas, as I mentioned. Right, as these continents come together, we have a budding of continents, which pushes up the rock layers. And the Himalayas, like I said, are a very good example of that. As plates, sometimes they'll slide past one another and nothing gets destroyed in those. That's perfectly possible, as well as what we call transforming faults, which means that they're moving in that ocean, that oceanic crust is moving. Just a little look at those. You see off the coast of California here, where we have a lot of activity, right, in the San Francisco, Los Angeles area. Now, keep in mind, plates and boundaries are always migrating or moving, right? We saw, obviously, the most movement one, with the break of Pangea. But as those continents move, remember, we have to keep in mind that movement is still happening, right? We have movement anywhere from one very small centimeter to about 20 centimeters a year, So we are still moving. All along here. So if we start at about 200 million years ago with Pangea, we can see the major movement here. 150 million years ago, still South America and Africa are still kind of together here. 90 million years ago, present day, we see the formation here of our main oceans of the world. Now we gathered our evidence, again, because of our ability to have submersible vehicles that could go down deep in the ocean, 1 mile, 2 miles, 3 miles down to the ocean floor, and they were able to map out the floor of the ocean. And this is where they got their proof or verification. Deep sea drilling, all that still happening today. It's not going to stop. We saw the hotspots of that created, for example, the Hawaiian Islands. That we know the Hawaiian Islands are a series of continents, or let's say here continents. I'm talking about landforms. So I don't know. I think there's 7 of them, 7 Hawaiian Islands, and each one was created by the eruption of volcano. Now, the hotspot for that volcano, right, stays in one place. So we have an eruption, we have movement, right? And we have another eruption and movement. So now we've got two islands, and the islands keep drifting. So the one that is furthest away from my hotspot is going to be the oldest island, and the one that is still over the hotspot is the newest of the islands. So, you know, that's what happens. The hotspot or mantle plume, whatever you want to call it, is what is creating an island like the Hawaiian Islands, which are all made from volcanic rock. And another piece that we use for evidence also is what we call paleomagnetism, right? We know that there is magnetism in that has been preserved in rocks, and we can look at the evidence of the movement of those rocks based on their magnetic fields, and that gives us some more information. So, here's some other information that we're able to track, right? The movement of the continents over long periods of time based on the magnetism inside the rock. Same thing under the ocean. Doesn't matter if it's above ground or below an ocean. So, as I mentioned, the Hawaiian Islands, and again, with the advent of GPS, right, global positioning system, we can pinpoint exactly where the island was today, 10 years ago, and where it's going to be 100 years from now, and 200 years from now, and 1,000,000 years from now, and so on. So there's a couple different types of heat that you can take a look at because heat and pressure are going to drive the movement of those plates. So, if you want to take a little look here at the forces that act, like I said, great pressure is going to cause movement and different types of heat layers. All right. So that's kind of where we're at with this this topic, plate tectonics, and normally if this was a longer class next week, we would have a whole week on earthquakes, but we don't have that much time, and I want to get a little bit into atmosphere and weather and things like that. So I have a video for you on earthquakes because as these plates move, right, we get more and more pressure that builds and builds and builds, and eventually there's a break in the plate, and that's what causes really the earth to start to shake. So make sure you take a look at that, and then I have the assignment, checked all the links on that, just to make sure everything is still working, and they are. So if you have any questions, please give me a line, drop me a line. If you're missing assignments, please get those to me as soon as you can, because we've got roughly 2 weeks to go in the course, and then the course will be over. So we don't want to leave everything to the last minute. So if you need me, give me a buzz. Otherwise, it was great talking with you. I will see you next week, week 5, with our new topic. Take care.